We are working on that to link it up, but it will mirror to the same site that we use at the BWRC, the same one that I gave you last time in class. Yeah, it's the same site. It will just alias to that. It it's I'm not sure. TAs are working on it, but we are working to resolve that. Yeah. Okay, good morning and welcome to E141. So what we're going to do today is review some of the ideas that we introduced last time and also continue through the introductory material and talk about design metrics a little bit. First couple announcements. You have your homework 1 due next week, and for that purpose you need to have Unix account on Cori. I hope all of you have Unix accounts by now. Is there anyone that doesn't have a Unix instructional account so far?
If you have a Windows account, would that be the same?
You still need the instructional account for the Unix machines. So if you don't have an account, please check this website. It gives you detailed instructions on what you do about opening an account, and that will allow you to log into these Unix machines and be able to do your homeworks. Okay, in addition to that, you will need PC accounts for 353 Cori, and we'll hopefully figure it out sometime next week when we settle with the enrollment list. And I'm thinking also to add another lab session so that you can all fit comfortably into that room. So it'll be probably 4 lab sessions, labs that are currently scheduled for Monday and Thursday. We will keep those, and we will probably add another lab on Friday and also another lab to either earlier Tuesday on Tuesday or sometime on Wednesday, but I will have to get back to you on that sometime next week because I have to check schedule of E105 because they have 6 lab slots, so they occupy quite a bit of space, so I need to coordinate with those folks as well. So discussions and labs will start in week 3 because next week is Labor Day. Yes.
I just want to point out, even though I think the 141 and the 105 it's separate, so you could probably run the labs at the same time.
Uh,
141 can be used on the back, 105 is kind of the front.
Right, but we have the question is, can we run 105 and 141 labs concurrently? And the answer is no, simply because we have space constraints. We have certain number of workstations there, and we can only accommodate about 25 students at a time. So we have to coordinate with 105. And for those of you who didn't have a chance to sign up last time, or for the new faces, I'm going to hand out the sign-up sheet again, and check if your name's already on the list, or sign up if you are new. And please give it back to me at the end of class. So with that, I will hopefully have the idea of the enrollments, and next week we'll be able to make some decisions about the class. Okay, so since there is no discussion sessions next week, I'm going to give you some help for homework 1. So in the next couple of minutes, I will spend some time to get you started with HSpice, and this is basically all you need to know to be able to do homework number 1. And then TAs will later help you in their discussion sessions with more details, more detailed explanation of HSpice that you will find handy for other homeworks as well. But for the first homework, is really simple. It's just basically calibration test to make sure that you have an account and that you're able to run HSpice and plot your results and turn back reports. So once you get instructional accounts and are able to log in, you have to run the simulator, and to do so, you have to have your SPICE netlist that has some name .sp. It's very important that you have, it's basically a text file with the extension sp that the tool understands. And you can direct your output into a log file, in this case, with the extension lis. And in order to view the results of your work and SPICE simulation, you need to run this waveform viewer that is available through this command awaves. And as I mentioned, input files must have an extension sp, and the input file must also have this options post equal to specified. And what it does is essentially it enables you to save your simulation results and see them later on in the waveform viewer. And this also keeps your output in ASCII format. So you can specify post equal 1, you can have a binary format, and so on. But this is kind of convenient, and this will be something you will be using all for the rest of the semester. If you need help, if you're a new SPICE user, then there is plenty of online documentation available from the class website. And you can browse through the documentation, but keep in mind this is really large documents, almost 2,000 pages. Don't try to print it out. It's going to take a while. And there is also other resources. You may want to check the SPICE book by Andrei Vladimirescu. And I think this will be pretty much all you need to know to be able to execute your homework. On the class website, there are detailed instructions on where to find these net lists that you will have to simulate. So what you will have to do is basically you will start from a sample net list, and then you will have to modify that net list a little bit just for exercise, and then plot some results, and then turn in those results in your report. So this is a typical SPICE netlist format. It has several sections. It always starts with the first line treated as a comment, and all other lines are then comment lines start with either a star or a dollar sign. And what this netlist then has are first you have to have models of nonlinear elements that you simply include from this E141 folder. All the models are available to you. And then you have your circuit netlist, where you define your circuit topology, node connectivity, values of your source voltages and currents, and so on. And then you have some control statements. You have this to be able to save your simulation results. And then you also specify what kind of analysis do you want to perform. You can do transient, operating point, DC, And in this homework, you will need to do only transient and DC analysis, and it always ends with this .end statement. So it's quite simple. You basically have to understand the structure. The input files are case sensitive. That's one thing to keep in mind, but you can read plenty of that in your documentation. The comment lines, and also all nonlinear devices must have a model statement that is basically included in this model file. So in this class, you will have to work with quarter micron CMOS models. And especially for the first homework, you will also need to include this BJT model. That is your netlist RTL inverter that you have to simulate initially, and then you have to modify that BJT to replace it with a MOSFET, and then do the same basically and turn in your report. So the models are all located on instructional machines in this E141 models account, and you will be using NPN model BJT for the first homework, and for the rest of the class, quarter micron CMOS G25 models. There is a number of machines in the instructional lab that you can log into, and these are just some suggestions for the machines you can use: Cori, Quasar, or C199.ECS. And I think this is pretty much all you need to do, all you need to understand to be able to do your homework number 1. Do you have any questions about homework? Yes. Please use the microphone. I will repeat the question. So the question is it possible to set up home computer to work remotely? And the answer is yes. You will find in 353 lab that you can nicely log onto terminal servers from the Windows machines, and then you can also log into the same terminal server from home, and then you can simply SSH to one of these instructional machines and do your work from home. Yes.
This quarter micron CMOS model, it is specified as G25.mod, but in the second part of the homework, there's a model named as SCMOS.mod. Is it different from this?
That's right. That's a good question. So the question is if this model G25 mod is different from the NMOS model that you will be using in the second part of your homework. And the answer is yes. This G25 mod is basically level 49 model with large number of parameters that model various transistor effects. And in your homework, you will be simply using that NMOS model that will be basically defined on that line. When you declare your NMOS and then you say NMOS and give really simple parameters that you will use for that homework only.
Is it possible to have a look at the model parameters in the E141 model, so how that model file is specified?
Absolutely. So this is a text file, and you can look through the model file and then see what's included. There is quite a bit of parameters, so it'll be a good exercise to look into it. Also, another announcement, TAs have enabled a news group. We decided to go with the Google News Group because that's readily accessible from everywhere, so you don't need to be tied up with the EX domain. And so please use the discussion forum, ask questions, and have discussions there. Okay, good. So last time we talked about Moore's law and the historical evolution of digital integrated circuits, and also some challenges in digital IC design in the next decade. And what we are going to do today is review some of the main concepts introduced last time, and also continue with the introductory material and introduce some quality metrics for a design that you will be facing for the rest of the semester over and over again. So just briefly to review, this is basically the main idea that we talked and discussed last time that addresses rapid progress in complexity of integrated circuits. And we looked at some historical examples. First microprocessor here shown on the left that was introduced in 1971. That was a fairly simple design from today's perspective, only 2300,000 transistors, 100 kilohertz operation. And then what happened over the period of 30 years, we had dramatic increase in complexity and performance of these devices, which ended up with a recent design of Pentium 4 shown on the right-hand side. And what was notable difference apart from complexity in these designs is also evolution of automated ways you can build certain blocks in a design, and basically EDA evolution that enabled you integration of a very large number of components onto a single die. So this was basically handcrafted design. This was a design that was built out of standard cells and modules. So you can see a lot of standard cell arrays here. You can also see memory modules that are packed around here and so on. And this was quite impressive progress that's been going on for the past over 30 years now. And here are some of the main takeaway points that we introduced last time. So more identified with increase of number of transistors per year. And we've seen last time that the number of transistors that can be integrated on a single die increased about 2 times every 2 years. So that's point number one. Point number two, to sustain Moore's law, we had to increase logic density also on the same 2x trend. And normally, a lead microprocessor designs would be ported over to 2 consecutive technology generations, and those designs are called shrinks and compactions. They also meet density goals, and also new microarchitectures introduced drop density with respect to the previous generation. To satisfy Moore's law, die size grew about 2 times every 10 years, or 14% every 2 years. Frequency in microprocessors first rapidly increased, then leveled off, and then picked up again at the 2x rate when NMOS implementations were replaced with full CMOS designs. So the takeaway point here is also lead microprocessor frequency doubles every 2 years. So important number of transistor doubles every 2 years, frequency doubles every 2 years, and die size increases by 14% every 2 years. So what enabled this Moore's law is improvements in manufacturing technology that reduced defect density that we will talk a bit about today, and therefore the cost of a die didn't increase much. And also we have to attribute this advancement to shrinking of transistor dimensions, and also design cleverness and new circuit ideas. So with increasing frequency and the number of components on a die, what happens with the processor power? It increases as well. And as we discussed last time, it increased rapidly up to 0.8 micron technology, where we had constant voltage scaling. And then due to power reasons, people decided to do constant electric field scaling, scale down the supply voltages along the way as well. So it kind of leveled off. And shrinks and compactions also reduced power consumption for the reasons we explained last time. So processor power increases point number one, compactions provide higher performance at a lower power. So if you continue to do business as usual, power will continue to increase and it will be a problem. So the problem here is heat removal and power density. So what happened also over time to be able to support this increase in complexity and number of components on a chip, we also had to develop more sophisticated design methodologies and work a lot on electronic design automation to be able to bridge this gap between increased complexity of a component and productivity of designer per month. That was also going on at an exponential rate, but not as much as the complexity requirements. So the complexity outpaces design productivity. So okay, so this is a summary what we've discussed. Basically, the technology scaling happened every technology generation by about factor of 0.7. You would scale your device dimensions, width and length. You would scale also transistor threshold, transistor supply voltage. And as a result of technology scaling, the number of transistors per die double every 2 years. Basically, with this scaling by a factor of 0.7, we can integrate the same amount of functionality in 2 times smaller area. And therefore, the cost of a function decreases 2x. So the main problem with that is, as we saw, power delivery and power dissipation. And that is becoming a main challenge in designs today and a problem in the future. So now the question is also how to keep designing these more and more complex chips that perform complex operations because designer productivity does not double every 2 years. And the answer for that was, as we saw last time, is that you need to understand different level of abstraction and sort of simplify the problem, abstract things, treat your design components as black boxes and have some macro models that you can propagate across design of multiple layers of design abstraction. And this also led to the development of automated tools that aid in design of complicated chips. So these are the abstraction levels that we discussed last time. So what we've been doing is basically last time we started from large-scale examples such as microprocessors to just understand the whole concept of migration in technology over time and increasing complexity, frequency, power, and so on. And what we are going to do today and is going to go down this hierarchy and introduce some cost metrics, mainly at the gate level, but the metrics that we are going to introduce today are applicable to all of these levels. And then finally, in the next lecture, we will start from the fundamental device physics and then go upward in the hierarchy for the rest of the class, build on the ideas that we developed. So this is still introductory material this week. So if we keep scaling the technology as we did in the past, doubling performance every 2 years, doubling the number of components on a chip, then by year 2010, the prediction is that we will be able to have machines that execute about 1 tera instructions per second that will run on 20 to 30 gigahertz clocks, the complexity of about 1 billion transistors on a die, single die, with a die area of 40 millimeters on a side. And clearly, if we continue to double the complexity, double the frequency, what's that going to mean for the power consumption? Apparently, power is going to increase as well. And if we just keep that scaling trend, we will have very large power dissipation numbers of the order of tens of kilowatts. And also another problem that we'll talk more about later in the class will be leakage power, increasing importance of leakage power, because that power is dependent on the threshold voltage in an exponential fashion. So if you keep scaling your threshold voltages aggressively, then you're having exponential problem in leakage power. So clearly, these power levels seem a little bit unrealistic, as someone has pointed out last time, and we will have to find alternative solutions that will enable us to sustain this complexity growth. Okay, so that was about a recap of what we did last time, challenges of today's digital integrated circuits, how does this project into the future, and then with that I will now go into a new topic and discuss design metrics. Do you have any questions? Questions? No questions. Good. Okay, so there is really 4 things that you need to remember today. These are really important design metrics, and I will introduce concepts of cost of an integrated circuit, reliability, we'll talk about noise margins, and we'll talk about the way we characterize integrated circuits in terms of performance and also power consumption. And today we will just give you a conceptual story of what all of these parameters mean, and give you some hints what do they mean at the gate level. But these are the parameters that will keep coming back to over and over again in this class at various layers in design abstraction. So it's very important to understand the definitions of these parameters. Okay, ready? All right. So the cost of any component can be divided into 2 components. Those are recurring expenses or variable cost, and non-recurring expenses or fixed cost. So non-recurring expenses are those that are independent of sales volume of a particular product or number of products that are manufactured. So this is sort of a one-time fixed investment for actually a range of products. And fixed cost in designing a product obviously has to deal with effort of a design team, engineering team that is spent into producing the design, mask generation, and that is a big factor of this fixed cost of a design. So obviously if a design has more aggressive specifications, higher complexity, that will increase this fixed cost because it will take more time and effort to produce a design. Also, if you have more skilled engineering team, that will also help. If you have more sophisticated design methodologies, that will also help to do a better job and reduce the cost of your design. There may be also, in addition to that, so that's the main component of this fixed non-recurring cost. And there is also, in addition to that, there are indirect costs that are not necessarily associated with that particular product, but they're associated with company operation in general. So that may be research and development expenditures, manufacturing equipment, setting up infrastructure for testing, and so on. So that's fixed cost. And then in addition to that component, there is this variable cost. And variable cost is proportional to the volume. It's proportional to a chip area and the complexity of design that needs to be manufactured. And the main components of this variable cost are related to manufacturing the design, then design, assembly, and packaging, and finally performing a test on a component before it can go into production. So it's really 2 components: fixed cost, design time and effort, mask generation, company overhead doesn't depend on volume, it's one time, and then the rest is proportional to volume and chip area. Okay. So non-recurring cost is increasing, and shown in this slide is non-recurring engineering cost in terms of mask cost as we go over different process generations. So basically, to provide a set of masks for manufacturing process, it will cost more and more in time. Since this cost seems seemingly large, then it does make sense to invest a lot of time and have a big engineering team working on a large volume successful product that will bring the variable cost down, as we have seen in the microprocessor industry lately. And what is mask? Basically, we will talk about that later in the next lecture. And basically, just to give you a rough idea, so mask is a sort of interface between your production facility and your design. So it's basically a set of patterns that you put on your across your chip that will be able to be translated into your design. So the total cost of integrated circuit is the sum of these two components. So you have variable cost, and you also have this fixed cost that you divide by the volume. And this variable cost, as we said, is dependent on the cost of a die, cost of packaging, and testing of the die. And it's also inversely proportional to the final yield, because not all the dies that are fabricated are fully functional. So you have to discard those non-functional, malfunctioning dies and account that into your variable cost as well. So what this expression tells you is that you have, for a large volume products, you have basically averaging out this fixed cost, and so the goal is now to reduce this variable cost as well in order to be able to minimize the cost per the total cost per integrated circuit. The questions? Everything clear? So okay, so takeaway points here. So small volume products will tend to be more expensive than the large volume products because of this relationship between the different cost functions. So let's now examine in particular cost of a die. What does it take to fabricate a design? So die cost is basically determined by the wafer cost, the cost that you need to have to manufacture silicon wafer, as shown here. And on the wafer you have and after your wafer is manufactured, you slice up the wafer into dice. And so the cost of a single die is equal to the cost of the wafer divided by the number of dies per wafer. But it's not only that, the number of dies per wafer, it is also important to factor in separate the good dies from the bad dies. And typically the wafer size has been between 4 and 12 inches, and today it's mostly 12-inch fabs, and you'll see this in much more detail in the next class. So important here to understand it's wafer cost, you have certain number of dies, and you have a yield. So what is yield is a number of good chips per wafer versus the total number of chips that are manufactured in the same run. So the number of dies per wafer can be calculated using this simple formula. So the problem here is that it's not simply the area of the wafer divided by the area of a single chip, because wafers are round and the chips are square. So you have to discard first the wafers that are around the edges of the dies that are around the edges of the wafer. And apparently, if you have smaller dies, then you will end up with more efficient utilization of your wafer. And the wafer size has been increasing over time, so we are converging more toward this case. So this is the total number of dies per wafer. So now you also need to account for defects on those dies those full dies that happen to be manufactured. And those defects may occur for various reasons, but it's mostly due to manufacturing process. You eventually incur some faults in your design, and that's why it's important to do full test of each of the chips that you get out of fab to be able to figure out the yield and sort out the bad components, discard the bad components. And apparently, as you see from this illustration here, when your die area is small, then you have a better yield. And when the area keeps increasing, then chances are that you will have more defects in that particular area of your design. And there is also a model for this die yield that depends on several parameters. First, defects per unit area are randomly, uniformly distributed. And they're about 1 defect per centimeter square on a wafer. And then in addition to that, you have the complexity of manufacturing process, and that will ultimately determine the number of faults that you have in your design. And it's given by this a relationship here, that the die yield depends on the number of defects per unit area times the die area divided by this complexity parameter to the negative alpha. And typical numbers for this complexity of manufacturing process is about 3. So with this previous formula, we had that. So there is a strong relationship between die cost and the area. So smaller area designs will apparently have will be cheaper. So you have this expression here that die cost is inversely proportional to the number of dies per wafer can you please switch the camera to Okay, so the die cost is inversely proportional to the number of dies per wafer, and it's also inversely proportional to the die yield. So how does area factor into this picture? The more dies you can fit on a wafer, the smaller the area. So this is sort of now proportional to 1 over area, that's the number of dies, and then we had this exponential relationship where we had area to the -3, so we had 1 over A3. So roughly the die cost is proportional to the area, is a function of quadratic function of the area in a sense. And a large portion of that die cost has to do with die yield. Okay. So can we go to slides back, please? Thank you. So here are some examples of microprocessor designs as of 1994, and die cost is calculated as wafer cost divided by the number of dies per wafer and die yield. So you can clearly see that impact of each of these parameters on the total cost. So for example, we can take a look at these two examples that have similar number of dies per wafer, similar wafer cost, defects, and similar area, but due to the difference in yield, we have over 2 times larger die cost. So this is just to give you understanding of the dollar cost to produce a certain design. Okay. So as a result of all of this, the total cost that it takes to produce a single transistor has been also declining exponentially over time. And today, you can produce about 5 to 10 million transistors per dollar, or the cost of a dollar is the cost of a transistor is about 100 nanodollars per transistor. I don't know if that unit is kind of familiar to you, but it's quite small, and it will keep decreasing in the future. So far for the cost. Do you have any questions about the cost? So we had fixed cost, variable cost, and we also had to understand the cost of a die and yield parameter. It's very important. Okay. So now we will discuss a little bit about reliability of a circuit, of a design. So when you make your design, you would ideally expect that design to operate in a certain desired way. You would expect your voltage levels to be at the certain value, but in reality that doesn't really happen, and there is a number of reasons why you can have deviations from your ideally desirable values, and that is attributed to noise. So you have various noise sources that can basically do some sort of a damage to your useful signal levels, and that can eventually corrupt your signal and compromise your circuit behavior. And that's a very important issue and one of the challenges in submicron design. So it's very important to understand the reliability and noise issues in digital design. So there is a number of sources of noise, and just as an example, on this diagram, you can see that if you have 2 lines running in parallel next to each other, then they exhibit inductive coupling and also capacitive coupling. So when a signal on one line changes, that also affects the signal on the other line, and that may affect your voltage at that node. Similarly, the current change in one inductive branch will couple to the other, and then you may have some unwanted current and at your circuit. Also, you may have some power and ground noise on your power and ground lines, because you may think that you have turned on your circuit to work at 1 volt, but in reality you have really dittery signal, varies over time for various reasons. And most of these noise sources are internally generated inside the circuit, that are intrinsic to the circuit configuration, and those are typically proportional to the signal swing. So for example, if you have your signal going to 0 to VDD, then you can expect your noise at this node to be somewhat proportional to that signal swing. So we normally express these internal noise sources in terms of a percentage of a signal swing that is desirable. And then you can also, in addition, you have external noise sources that are not related to your signal levels. And those noise sources are typically expressed in terms of a fixed certain amount of voltage and certain amount of current that is present in addition to your useful signal. So now, how do we quantify the quality of a gate to work in a noisy environment? In order to do so, we have to sort of understand the discrete behavior of a gate and the way we map electrical characteristic of a gate into Boolean signals, into logic 0 and 1. So we have mathematical concept of logic 0 and 1 on one side, and we also have practical implementation of a circuit that implements that 0 and 1. So we have to assign certain signal levels that will correspond to 0 and 1 that is expressed in terms of real electrical signal, like a voltage or current. So in order to do so, we need to understand DC or static behavior of a circuit. So over here we plot DC transfer characteristic of an inverting gate in this case. So we will develop most of our ideas on an inverter example because that's the major building block in digital circuits. And once you understand inverter, you can understand all the gates. So this graph plots the output voltage of an inverting gate for a range of possible input voltages. And on this characteristic, we define some nominal values that we assign to logic 0 and logic 1. So the nominal value to assign to logic 0 is called VOL. So that's the output low voltage that we interpret as logic 0. And similarly, we have VOH, that is high value of output that is assigned to logic 1. And this voltage transfer characteristic is described in the blue line with this function f. So basically, when you work with nominal values, when you have an inverting gate, if you have VOL or logic 0 at the input, you will have VOH or logic 1 at the output, thus providing inverting function. Similarly, when you have VOH at the input, VOL is this function, transfer function of VOH. And in addition to these nominal voltage levels, it's also important to define this switching threshold that can be simply found by drawing a 45-degree line here on this voltage transfer characteristic where output voltage is equal to the input voltage. And that is the threshold that will be related to switching events in a gate, as we will see later in the study of systems with or without feedback. And keep in mind, this switching threshold doesn't have anything to do with the transistor threshold, threshold of a transistor used to implement a function. So now the question is, what happens if your input signal deviates from this nominal value, and how much of deviation you can tolerate? And in order to understand that, we will need to introduce noise margin concept to be able to quantify the ability of a gate to work in a noisy environment. So what this noise margin tells you is basically how much you can deviate from this nominal value and still be able to interpret your output signal as either logic 0 or logic 1. And for that purpose, we will also define this VIL and VIH signals. And they correspond to this 45-degree slope on a voltage transfer characteristic over here. So you have nominal values, and you have also this VIL and VIH. So V input low is the maximum voltage at the input that will still be propagated on the output of a gate and be treated as valid logic level. And then in between these two undefined region, that is undesirable region when you don't want to be accepting transient regime. So when you transition between 0 and 1. So now the question is, what happens when you apply and deviate from this ideal value and then sort of accumulate noise in a consecutive stages? That's what we are going to see in a moment, but first define noise margin. So this is very important concept to understand. So you have this work between these nominal values, and so you need to make sure that the output of a gate, when it's driving the next stage, when corrupted with noise, will be still interpreted as logic 0 at the input of the next gate. So the difference between these two values defines noise margin low. And similarly, when you are driving your gate with logic 1 from the previous stage and then driving into the next stage with some additive noise, you would still be able to interpret that signal as a logic 1. And this is the minimum voltage level that your input accepts as logic 1. The difference between the two is noise margin high. So now you would apparently want to have each of these noise margin numbers as high as possible, because that will give a lot of room for your gate for this noise. But then it's not really only the size of this bin, but it's also the robustness of a gate to noise sources. So in this, when designing your gates, you would need to allocate certain noise margin to expected noises of source, so to make sure that your gate is robust. And the sources can be various. You can have a power supply, you can have offset. Basically, you can model your digital system with noise as like a transmit receive type of configuration, and you may have offsets in transmit and receive parameters. Then you can have crosstalk, where you can exhibit either inductive or capacitive effects. Then you may have interference between the signals when you send consecutively various signals across the lines. Then you may have some interference between the neighboring signals that are interfering with each other. Then we will have a timing noise, where you have basically jitter and skew. And we will come back to these noise sources in more detail in the class when we talk about transmission lines and interconnect, and also when we talk about timing issues in sequential circuits. And you also need to differentiate between fixed and proportional noise sources. So this is what you need to remember. You have to remember noise margins, the types of sources, and the origin of these noises. So as I said, absolute noise margin values are sort of misleading, because sometimes you may have, for example, a circuit with a large noise margin, but it may have, for example, very high impedance. And if you are working with voltages, then you would like to have your voltage level sort of really solid and stable voltage level. And if you have a high impedance, what does that do to your voltage? It's very sort of unreliable, so you can drive that signal away from its desired value. So obviously you would want to have very low impedance at that node so that it really exhibits properties of a voltage source and that it provides really good solid voltage at that node. And then we will see how this applies later on in studying of different logic families. You will have, for example, dynamic nodes which have floating nodes, and we will also study static circuits which will have all the nodes connected to low impedance ground or VDD at all times. So noise immunity, in addition to the noise margin, is very important metric. So that tells you about the capability of your circuit to suppress noise sources. And some parameters that you need to worry about are apparently input impedance of the receiver, output impedance of a driver, and noise transfer functions. So you can do the noise model the noise analysis as the sum of all noise sources with gain functions from various noise sources, and you can sum them up all at the node of interest and perform an analysis of that. So obviously when you have higher impedance of the receiver, that's good because it doesn't provide a lot of loading to your previous gate, and it doesn't doesn't affect much your signal levels, and it's also very desirable to have low impedance of a driver because that provides really solid voltage levels to the next gate, and also gives sufficient drive capability. Okay. So let's see what happens now. It's interesting to analyze the case where you have a chain of gates, and each gate along the chain may deviate from its ideally desirable nominal voltage level. So you may have gate at stage I that has certain noise that gets propagated to the output of that gate, and then you have additional noise source, the output of the gate, that gets propagated through the chain of gates. And the gate will always recover to fixed voltage level 0 or 1 if it possesses regenerative property. And in order to analyze that, so we basically plot voltage transfer characteristic of a gate that's described here with this function f of v, and this is a solid line in this graph. And you also model the next stage with its inverse transfer function, because what you do here basically is that for the gate in stage I, you have output versus input relationship, but for the gate in stage I plus 1, you have input versus output. So it's kind of reversed. And the way you figure out these levels here, you have, let's assume that you have gate in stage I that is corrupted with some noise, and its value deviates from the nominal value. So let's assume that its value is V naught. So I'll actually go back to the overhead to explain you this a little bit further. So we have input to the gate, and we have output. This is the transfer characteristic. and then you also have this mirrored transfer characteristic. So let's assume that we are somewhere here at the input of a gate in stage I. So we have voltage level V0. So we go over here, and that will produce V1. So we have V1 is equal to F of V0. So then this V1 is the input to the next stage, and then it will produce voltage level V2. So basically we have that V2 is inverse function of V1. And then you continue forward, and then you go to the next stage. You have V3 and so on. So you basically converge to either logic 0 or logic 1. So depending how many stages you have in this circuit, that defines if you end up with logic 0 or with logic 1. So if you have even number of stages, then you will have non-inverting function. If you have odd number of stages, then you will have inverting function. And for this gate that always ends up in one of the stable states, 0 or 1, we say that it has regenerative property because it's able to recover from the noise disturbances and settle to a fixed value. The question, yes?
So this assumes all the gates along the chain have same voltage transfer functions,
That's
right?
correct, yes.
Is that a good assumption in real life? Or
Excuse me?
is that a good assumption in real cases? Is it pretty similar?
So the question is if the gates give the same transfer characteristic, is that assumption in real cases? In some cases it is, in some cases it's not. For most practical cases it's a good assumption. When you're, for example, working with a chain of gates that implement, for example, a clock tree, you have commonly a situation when you need to analyze a buffer tree that is built out of inverters. So you have a chain of gates with the same property, and then you can basically just assume that they all have the same transfer characteristic. If not, then you have to work apparently with transfer characteristic of each individual gate, but that still follows this analysis, this concept in general. Okay. So what provides this regenerative property is this gain region here, that you have a gain on absolute value of a gain greater than 1 in this transition period. So let's go back to the slides. If you have, if you assume a transfer characteristic with a gain in this region less than 1, then you would eventually settle in this undefined region where you neither have logic 0 or logic 1, and that's basically how you end up there. So it's very important for gates to have gain to be able to sustain noise. So shown here is the example of regenerative circuit when you have a chain of inverters, and then you have start with the logic 0 at the stage 1, or rather logic 1 that doesn't have sufficient signal swing, that gets recovered a little bit in this stage 1, and then that gets almost fully recovered in stage 2. As you go farther along the chain, you get closer to your nominal values. Some other parameters that are really important as well are fan in and fan out. So fan out of a gate represents a number of gates that are loading the output of the prior stage. And apparently the larger the fan out you have more loading on your gate, and that might affect your noise levels, the quality of your signal. So what's highly desirable is that all these input impedance to these gates will be high, such that loading effect is as small as possible, and also that the driver impedance is as low as possible, so it's able to deliver current into deliver enough drive into the inputs of the next stages. And the fan out is simply quantified by the number of gates that are sort of hanging off of the output of your driver. There is another parameter that's called fan in, and that simply tells you the number of inputs that you have into a gate, and then it tells you what it explains is basically the complexity of a gate. We will see later on that you can implement certain functions in different ways. You can, for example, implement 4 input AND function as a single gate, or you can implement it with using 2 input gates and so on. So it tells you about that. So now, having all these definitions in mind, it is important to understand what's the ideal gate. What are the properties that we have in ideal case? And although this is not really practically feasible, it's important to understand what ideal gate means so that we can quantify other gates with respect to this ideally desired behavior. So ideal gate would have infinite output fan out. It will have infinite input impedance because it provides it doesn't provide any loading to the previous stages, and it will have maximum drive capability, which means output impedance will be 0. And it will have noise margins at VDD over 2 because the voltage levels will be at 0 and VDD, and this transient region will happen at exactly VDD with infinite gain. So you basically have really like nice gate. And while, as I said, in most practical cases, this is not possible, there will be some gates that exhibit behavior that is quite close to ideal gate, and you will see that when you get to study inverter voltage transfer characteristic and simulate, analyze some CMOS inverters. Okay, everything clear so far? Okay, so here's the transfer characteristic of an NMOS inverter with a load. So it has large noise margin high and low noise margin low. So let's do a little exercise here on the overhead just to sort of refresh of what we've just discussed today. So if you have V out, this is your V in. This is your voltage transfer characteristic. If this was defined as VOH, then we have this VM, and then we have this also VOH. So I'd rather put this one at VOL. And if this is noise margin for the high, logic 1, and noise margin for logic 0. So now, if you have nominal value at the output, what value should stand here at the input? What do you need to apply to get VOH? VIL or VOL? VIL? VOL? Okay, so that's actually could probably be argued that's right, but this is actually VOL here. because that's the way we define things. If you have ideal nominal values VOL and VOH, if you apply VOL, then you get VOH at the output. That's by definition. And then working with this noise margin, if you have noise margin defined as here, then what would be this value? VNI? How did we define noise margin? So noise margin H is equal to, so we have VOH minus VIH. So we have VIH here, right? And also similarly for this value. So VIL. So basically that's important to understand, and that, for example, VOH is not a function of VIL, but rather VOL, simply because that's the way we introduce these terms. And that's oftentimes confusing, but it's important to understand the definitions and just stick to them. And then you have, starting from this VOL, then you have certain region over which you can tolerate noise and still have logic 0 treated at the input, and also over here you have logic 1 with some noise. But when you apply any signal in between this VOL and VIL, then you end up at some output. So basically your output would be a function. So let's see, we are here. So you have V out is equal to F, and this is a transfer function F of this value here, V, let's say just VL. So it's some low that it's interpreted as logic 0. So it's function of VL, and then as you go, for example, put these gates in a chain, then you would end up with a fixed voltage even here to VOH. It will converge, eventually settle down. So understand these definitions. It's kind of important to realize. All right. So now we will introduce the concept of speed. You can speed or performance of digital circuits, and this metric can be quantified in many different ways depending on which level of abstraction you're really talking about. For example, at the full microprocessor design level, you probably associate performance with the number of useful instructions that you can perform over a period of time, number of instructions per second, or you can define the quality of microarchitecture by how fast it can be clocked, how many stages do you have in between pipeline registers, and going even more down, you go to the gate level where you define a propagation delay. So basically this metric will be recurring in this course at various levels, but it's very, very important to understand the speed in terms of propagation delay of a gate, so we can expand this concept further up to the higher layers in design abstraction. To provide delay definitions, we look at these waveforms. So let's assume that we have an inverting gate, because we said we'll try to define everything on an inverter, really understand this example. So let's assume that at the input we have a waveform that goes from 0 to 1 and then goes back to 0. And then the output will, as a result of this input waveform, the output will provide inverting function with some delay. And this delay is associated with traveling over that voltage transfer characteristic through that transition region and so on. It takes some time to understand the information from the input, and it will then finally settle to logic 0. So the time it takes a gate to process this information, and the time it takes this input signal to go between 50% of transition and appear at the output. So this distance between these 50% points is called a propagation delay for high to low output. And this is again sort of definition issue here is that you can define HL relative to the input or to the output. So in this case, you can say this is maybe TP LH because input is rising, but we always refer to the output case because sometimes you may have inverting gates, sometimes you have non-inverting, and so on. So we define our delay numbers relative to this output. And so this defines your falling transition, and delay experienced by the falling transition at the input, which will cause your output to undergo a rising transition, is called TPLH. So these two delays really have some physical meaning because you know that's the time it takes to produce a falling or rising transition. And oftentimes we also compute the average of the two delays, and then we say this is a propagation delay associated with the gate. And although this number has no physical meaning, it provides you relative ability of a gate in terms of gate delay, in terms of speed for that technology. There is also other parameters that factor into this delay formula that we'll talk in much more detail, but just to introduce the concept here, apparently if you have more fan-out loading, it will take longer, right? Because you need to provide more current, deliver current to more inputs, to more load. And for that reason, we also define these rise and fall times. So if you have a lot of load, your rise and fall times will be longer, and that has to do with your signal slope. So rise and fall transitions are defined between 10 and 90% on output waveform, the time it takes for output to go between 10 and 90%. And again, these are all definitions and conventions. Sometimes people define rise and fall transitions between 20 and 80% and so on. But this is basically the way you calculate propagation delay at the gate level. Sometimes it's very useful to sort of understand also the capability of your technology, how fast your gates can run, because this propagation delay is typically expressed in picoseconds, and it doesn't really mean much when you scale technologies. When you port your design over to a new technology, then apparently you will have faster gates, and then that doesn't really mean that your design is better and faster than it was in the previous technology. So in order to, so the gate delay obviously depends on the gate topology, also depends on technology. So to sort of eliminate this technology impact on the gate delay, people oftentimes use a ring oscillator as a benchmark circuit that really tells about the ability of your technology to provide certain performance. And this is simply a chain of inverters. You have to have odd number of inverters in a chain, and then you look for a period at any node in this inverter chain. You, for example, go falling transition at the input of this inverter, then V1 goes rising transition, falling, rising, falling, rising. That will catch up with this falling transition and sort of go around the circle. So for a rising transition to define the full period of oscillation of this oscillator, you'd need to go 2 times around the chain and calculate the propagation delay. And you have sort of averaging of TP LH and TP HL because you have a rising transition, falling transition, rising, falling, and so on. And then you just count the number around the loop. And if you have assumed that you have n stages around the loop, then the total period defined by this ring oscillator is 2 times the propagation delay of your gate times the number of gates in a chain. And that way you can calculate your propagation delay of your inverter. And then you say TP is equal T divided by 2N. And apparently, in order for this experiment to work successfully, you have to have your propagation delay total period actually such that it is much greater than the rising and falling transitions, because you want to make sure that you have enough time for all the transitions to settle. Otherwise, you may dampen the oscillations and the oscillator may die out. Get a question?
Why does it need to be an odd number of gates?
Why does it need to be odd number of gates? That's because if you have even number of gates, let's assume for simplicity you have two number of gates. You have logic 0 here, logic 1 here, logic 0 here. You're dead, right? So in order for this to oscillate, you have to kind of keep pushing around the loop. And this is really a good circuit to sort of give you a first-hand understanding of the capability of your technology. But when you calculate a propagation delay of this inverter in this configuration, it's really not very useful number, because you can calculate, for example, 20 picosecond delay. That doesn't mean that your design will be able to work at 50 gigahertz, because there is many other things that affect the speed of operation at the higher abstraction level. For example, you would likely have fan-out higher than 1, and you will have more complex functions to implement than a simple inversion. And you may also want to have a chain of gates to implement something useful. So typically, you have about 20 to 50 times less for a clock cycle than provided by this inverter chain. And I'll just finish with one more metric here. So in order to really understand the capability and the quality of your design, and to be able to compare and scale across technologies, it's also very important to understand this fan-out 4 inverter delay metric. Because as I said, the previous examples was just to calibrate the technology, how fast you can go. But what this metrics tells you is really like more realistic environment, when you have some loading at the output, and typically you drive about fan-out 4, that's good for the speed reasons. And then you typically normalize the delay of your data paths to a fan-out 4 inverter, because that tells you about the quality of a design. For example, 64-bit adder when designed for the high speed is about 7 fan-out 4 inverters. So people can't really trick you when they say, oh, I have this design that's faster than yours, but yes, you have better technology, so how do you know? And that's one of the ways you can really calibrate the delay performance of your circuit. So I guess I will just stop here, and next time we will finish up with metrics and go with introduction to manufacturing process. Okay.